not the same.
Okay. So basically what we did here is just kind of, this set of Gaussian integers, which we went over in class. Does everybody remember what Gaussian integers are? That's just showing what Gaussian integers are.
Wait, Z and what?
Z of I, that's a set of Gaussian integers.
It's not a Z adjoint type. Z adjoint means the Z and they throw one element I, it turns out they add and multiply and they go Z adjoint type.
So we used a lot, we used this thing called norm, and that's expressed in this way, N of G. And that's just A squared plus B squared, because G is A plus BI. So we take this A and B, square them, add them together, that's the norm. Not the squares.
What does norm mean? Make a picture. Might tell people to do it.
Sort of. So if you take any,
One of them has to be I.
Alright, so basically the definition of a norm is if you take any Gaussian integer and plot it, the norm is going to be the distance from the origin squared.
You guys agree?
Because if you have this is A, and this is B, so this is square root of A squared plus B squared. So it's basically taking the distance and getting rid of the square root. So we had a bunch of just calculating the norms. And so we had some that have the same norm. Alright. All these Gaussian integers have the same norm. Yeah, just do one of those. That was several.
I have a question. Do you plot the norm on like the x-axis?
Plot it on the
what?
coordinate plane.
You don't plot it on
The norm is this distance for any Gaussian integer squared. Distance from the origin. So then we plotted a bunch of the norms. Or a bunch of the Gaussian integers, which have the same norm. So that's
I want a better marker.
is that marker good or? So the question was, does norm have something to do with the Pythagorean theorem? So we found that yes, because we draw the lines to connect them to the origin. The right triangle can be formed. Right triangle can be formed by and like David said, the hypotenuse is square root of A squared plus B squared, or square root of the norm. Alright, so the next thing was just to get started. We filled out this chart for a bunch of different Gaussian integers. So could you write that down? Yeah. So there were a bunch. You can just have two of them here. This is our first Gaussian integer, our second, their products, and the norm box.
You got the parentheses in there.
Please add those in. I'll add this in the last meeting. the general.
Wait, for the norm of 2 plus I, is that S or A?
Uh,
Fine.
fine. Sorry about that. So we had a bunch more, but we're just going to show the general form. Yes, so the most important thing we got, well, I was going to go that. So the most important thing about this chart was that if you were looking at it, you may have noticed that the norm of G1 times G2 is equal to the norm of G1 times the norm of G2. So for this particular case, the norm of the products equals the product of the norms. So that was the first thing we tried to prove, that for any two Gaussian integers, if you multiply them together, the norm of that is going to equal the product of each of their individual norms.
Can you go with?
No, I proved it.
Yeah,
Can you go with?
yeah,
Yes,
the
ma'am.
the one that Nick's making is in general form. So if they're equal, then all the time.
And we proved it in 2 different ways.
Yeah, but we'll prove it again later.
Which way should I write down first? The normal way or the one using context?
I think the order will win.
Alright, so the first way was just algebraically, you can brute force it. And you could write all that out. Should I? Yeah, that's pretty much what it is right here. Wow. You could brute force it. Where you just brute force calculate the norm of this, and it equals this. And so that way is pretty boring. It's not very interesting. So the second way we decided to do it was by introducing a new term, which is next term is so basically, we the second way we proved it, which is a lot more interesting, is using conjugation, which is basically 2 Gaussian integers that where the first one is a plus bi and the second one is a minus bi. And so the geometric meaning of this, because we went over the geometric meaning of the norm, the geometric meaning of conjugation is a reflection over the x-axis. So if you have your coordinate system like this,
Well, we can have it up here, right?
yeah, I'll just use that one. Then 2 numbers that are conjugates are going to be reflected over the x-axis like this. So to do that, the way you prove that the norm of the products equals the product of the norms is
So what happens when we multiply something by
yeah, that's probably important. So when you multiply a number by its conjugate, you get, for instance, you have a number a plus bi, and you multiply by its conjugate a minus bi. You get a squared plus b squared, which is the norm, because it's because you have a squared here, and then this is minus b squared I squared, and I squared is minus 1. And then you have plus ABI, and then minus ABI, so it's just the norm. The product of the 2 conjugates is equal to the norm, either of them, because they have an equal number. Now proving it,
No, you're not quite there yet. Show that the conjugate of the product of the conjugate is the conjugate of the
okay then. So, yeah, yeah, well, you're right. So this is the conjugate. So the product, you take the conjugate of the product, it should equal the product of the conjugates. And so we did prove that. Alright, I'll just write it down. This is what I'm trying to do. It'd be nice if we could have this on the overhead so I could just go over.
By the way, it's a strange connection, isn't it?
Yeah.
The product of the conjugate, so you take the guy, you know. So x is multiplied by the reflection, and you get to know it. You guys explain, you guys get explaining? Take a number, right? Take the cosine, reflect the cosine section, multiplied by itself. And you get the-
Wait, no. I see.
I think it's kind of. How much noise is strange? Well, that's special multiplication.
Almost done. Alright, so basically, in order to prove that, you just take the, start with the norm of the product, and then you expand each of the Gaussian integers into a plus bi, and then you distribute it out, and then you get rid of the, you take the conjugate of that, the whole thing, and then you can factor it back into the product of the two, the product of the conjugates of the two Gaussian integers, not conjugates. Yeah. So now that we have this, you can prove that using that the product of the conjugates equals the conjugate of the product. You can use that to prove that the product of the norms equals the norm of the products. So over here, it's really short.
Do you want it?
Oh, that's why it's leak.
What?
See you later.
So this is the next thing you can
Answer say class possible. No, you're supposed to say love class possible.
No, my class is lower.
You got the shirt from
I can't read the back. I can't read the back.
Alright, so this proof is just one line. You take the norm of the product, and then you know that the norm, that the product of two conjugates is going to equal the norm of them. So then you can split this into just g1 times d2 times its conjugate, because that will equal the norm of both of them multiplied together. And then once again, you can split that up into g1 times the conjugate of g1 times g2 times the conjugate of g2. And then this just equals the norm of g1 times g2, the norm of g1 times the norm of g2. Because the product of these two is going to equal this norm, and the product of these two is going to equal that norm. Alright. What? Oh, okay.
You want to stop here because we know.
Alright. So these two
proofs were kind of dry, but they're very important for the later stuff we go over.
Tell us the idea of where you're going. What is it going to try to solve? What to do? Or to discuss? Because you guys both are doing the sum of the squares. This guy said ahead of time that we wanted to discover binary and triples and learn how to make them and how to.
Yeah, we're working with primes.
What are you doing?
Well, the thing that we're trying to do right now that we cannot do, I mean we can, but we haven't done, is we're trying to prove that for any G belonging to any G belonging to the set of Gaussian integers such that norm of G equals 4x plus 4 for x belonging to. There's a better way to say this.
Here it is.
All right, so any prime number that's
Any x.
That's an existence.
that's what it is.
Any x belonging to.
All right, so he can write it down. I'll explain. So what we're trying to prove is that any prime number in the set of natural numbers that is 1 mod 4. So for instance, 5, 13. That's 1 mod 4, right? Yeah. 17. Those ones. That all of them can be written as the sum of squares. Sum of 2 squares. Yeah. So like if you take 5, that's 1 squared plus 2 squared. 13 is 3 squared plus 2 squared. 17 is 4 squared plus 1 squared, and so on for all of them. And that's what we're trying to do.
This is just another way of saying it that it doesn't take, you can, if you start working, you can quickly see that it's the same thing. Any number that's 1 mod 4 in natural numbers is not prime Gaussian integers. Because basically we're saying that there's a number that can divide it. Because let's say we take 17. If we're saying that 17 is expressible as the sum of squares equals a squared plus b squared, then we know that we can take a plus bi and a minus bi and multiply them, and that equals a squared plus b squared equals 17, which means it's not prime because it has these two factors.
Amazing connection. Whoa. Strange connections. It's in the world of natural numbers and we can roll
But we have not been able to prove it.
We have
Very,
We know it's right.
Hey guys, 67.
For this case, you know that what you want your ratio of a to b to be here. So the line's going to look something like this. This is every point where a is negative 2b. So when yeah. We have a better picture here. So,
You can plot 2, 4. 2 plus 4.
So that's 2 plus 4i.
And gonna connect to 0, 0. Oh, now it's the same. Oh, right.
Because what happens is, then I did this in general, and we saw that the ratio of this A to this B very much corresponded to this ratio. I believe it was, and this 2A equals B, and this is minus 2A, so it's the opposite slope, which is why they're perpendicular. And you know it has to go through 0, 0, because 0 always works, so you can always find the line that works for that.
And if you take any point on this line, you can see geometrically what happened when you add.
Yeah. You get a parallelogram. A rectangle, actually. But, so if I pick a point like, say, 2 minus 1, 2 minus I, and I added these, I get a point on this parallelogram. This is 4 plus, well, it would be more like there. This is a rectangle though. This is form plus 3i.
Yeah.
Right.
And it forms a nice little rectangle. So that kind of makes sense. Because this times that.
Is that the diagonal?
Yeah.
Is that the diagonal?
Yeah.
Think about it. If you get a square plus b square, right? Because the right angle, it's, yeah. Beautiful. It's a fairly beautiful picture, unexpected. You see it? You see, one diagonal is a square plus b square equals the right triangle. It's square bracket. And the other one is the sum.
Okay. Wait, I don't know where you get your box from.
It's a rectangle.
Wait, why did you get why?
Because he's trying to find points such that the norm of the sum is equal to the sum of the norm. And the sum of the norms would be the sum of two squares and diagonal. And the norm of the sum would be the norm of the sub-diagonal.
So then the next thing that we wanted to look at was divisibility.
That's something with circles and inside circles.
So we say that G1 equals 33 plus 19x. And we want to see if it could possibly be divisible by any of these things. 1 minus 6i, 3 plus 2i, 3 plus 7i, and 3 plus 4i. But we already know that the norm of the products equals the product of the norms. The norm of this was 1450. The norm of A was 37. The norm of B was 13. The norm of C was 58. And the norm of D was 25. So, looking at A.
You might want to write prime factorization of 1450.
Yeah.
It's easier to say.
1450.
5 squared times 5.
So, obviously 37 does not divide it.
2 5 squared is what?
29.
Oh, 29.
So obviously 37 does not divide it. So let's say that there existed some Gaussian integer with some norm that such that A times this new G2 was 33 plus 19x. We know that the norms of this norm times that norm has to equal that norm. So 37 times x equals 1450. X kind of had better be an integer because all norms are, so you're dead. The same logic will apply for B. So without actually doing any trial and error division algorithm stuff, we see that these are both impossible. Now, 58, however, does divide. So we know that we need a number with a norm of 25 that will give us 33 plus 19. Now multiplying by 5 won't do it. And the only other thing with a norm of 25 is 3 plus 4i in some form. It could be 3 minus 4i, it could be minus 3 plus 4i, but something with a 3 and a 4. So we'll take it.
You might want to write on the left because you might need some space and you run out of it. Just right there on the space. Depends how you're going to do it.
3 plus 7i times 3 plus 4i.
Ah, you're going to do it this way. Okay. Then you can just do it in general. Oh no, you can do it in general.
Equals
You can do it in general.
9 minus 28.
Should I just turn this so you can, yeah.
Yeah, you already screwed with this one. So this one
No,
doesn't work.
this is 19. It's
Right, so it
still
doesn't work.
a multiplication by I.
Ah.
I mean, obviously this one doesn't work, but if I can multiply by I, I'll just multiply this by I or something. Plus 21I plus 12I. So we get minus 19 plus 33I. And I believe a multiplication by minus I fixes this. So we take this, we multiply by minus I.
No, I got minus
We
3.
get
Oh no, you see what?
we get 33 plus 99.
Yeah.
So then I just put that minus I multiplication in here. For minus 3. And that's 12 plus 21
Yeah, you good there.
plus
And 28
28 minus.
Yeah, you good.
So that works. So we found the factor that doesn't work. Looking at the next one, 3 plus 4i. We know that we need a number with a norm of 58. The only one that gets that
But could you
is...
continue from here? Because you already got some factorization, right?
Exactly.
So could you continue from
So
there?
when we already tried with 3 plus 4i, we got a number that worked. So now instead of plugging in that minus sign here, I'm just going to stick it in here. And we get 7 minus 3i. And that obviously will work. Because I just divided by minus I, multiplied by minus I. So D works too. But now we were wondering. We already knew that for one number, one Gaussian integer to divide the other, the norms have to divide. Because we showed that you're screwed otherwise. The question was, could we make it a double implication? Wasn't always true. And after somewhat stupidly spending like 3 days working on this, we realized it's obviously not true. Because, let's see, 3 plus 4i is not divisible by 5. But 25 is very much divisible by 25. So, we realized after quite a while that it shouldn't have taken us that long. Our problem was we were trying to prove it was true, instead of not
That
true.
would be a problem.
Yes. So,
You erase one in.
what?
So you erase one.
So, that's Now, this is where we kind of get more complicated stuff. I'm gonna erase them. Now, we need a couple definitions. So, G is if prime and Gaussian integers.
Low definition of prime, that's serious.
First of all, it had better be a Gaussian integer.
That's a good beginning.
Second of all,
It is a very important beginning. In order to be a black cat, you just get to be a cat.
G does not belong to the set of 1 minus 1i or minus I. Because then those would be the only primes because everything's divisible by all of them.
So that's one is not prime.
And any Gaussian integer with m dividing G Where G is
A
also
little,
down.
spread a little bigger. You become invisible.
So, if M divides G implies that where G is a prime, so G is belonging to the set of prime.
Okay. G is the one which you are saying.
Yeah. If M divides that G,
Uh-huh.
M is either implies M belongs to this set.
Oh, nicely said.
I didn't write this M wrong.
Nice. Now we just need to say it shorter.
So basically, M is not an associate of G because I have to define associate. It'll be easier to say in a second.
Yeah.
So we call
It's your own group presenting there.
Yes.
these are the units of Gaussian integers.
It's the same units as long time ago, right?
We just have 4 units
So those,
instead of 1.
right, those have multiplication inverse, and nothing else does.
And for any Gaussian integer that belongs on set of Gaussian integers, which they usually do, the associates of G are minus G, Gi, and minus Gi. These are what you get when you multiply G by a unit, other than 1.
So it's the product of the element by the unit.
Yes. So basically, our definition of prime is that a number is prime if everything that divides it is either its associate or a unit, which is true in most sets. It's divisible by basically itself in 1. There's
Yeah, that's exactly
multiple
what
copies of itself and multiple copies of itself. So, then we wanted to prime factorize 33 plus 99. So its norm, norm is 1450. So we realized that what we wanted to do was to find one Gaussian integer with each of these numbers as a norm, because that's as small as you can get. Like a 2, you can't get, no number will ever divide into something with a norm of 2, something with a norm of 5, or something with a norm of 29, because they're prime.
Excellent.
So our thing with a norm of 2 was 1 plus I.
But then you got to make sure that everything works.
Yeah,
Okay.
but we just multiply by
And you're sure that you're always
no,
going to be...
we're not always sure. Well, sometimes we have to switch a couple of things around. Times 2 plus
Umolali, you wanted to say that. Umolali, you seriously want to say that. You might need something like that a couple of weeks from now. In a very quick way.
This is what it ended up working out as. We had to multiply by some form of a unit to get this to work.
So that works, you think?
I believe so.
So 1 plus x is norm 2, 2 plus x is norm 5, so that's 25, and 2 and 5, that would be 29. So that part is good. Let's see if it really works. What's 2 plus x squared? 4, 3 plus 4i. Right?
Yes.
3 plus 4i. And that time 1 plus I would be minus 1 plus, no, plus 7i. Minus 1 plus 7i.
What are you doing now?
We think that times 1 plus I is minus 1 plus 7i.
Yeah.
And we're multiplying that by 2 minus 5i. And that would be 35 minus 2, 33. And 14 plus 5. Yep, that works. Go figure. So the question is, if you do it absolutely randomly, will it always work, or can you always tweak it?
No.
Is there any other prime factorization? That's the question.
Multiply. You can stick in units where you want, but
You sure? How do you know that? What if they're like genuinely different ones? For example, take 2 plus 5i and 2
If you
minus
switch it
5.
to 1 plus 2, then it has the same norm.
Right, but see, take 1 plus 2i, 1 minus 2i, write them down. They both have norm 5, agree?
Yeah.
Could you stick in some unit and make one into another one? Are they associates?
No, they're comprehensive.
They're not associates.
No.
So if I stick one of them in prime factorization, how do I get it to work?
I don't think you can.
So how do you know?
We messed up once.
So how do you know that one of them would always work?
What?
How do you know that one of them would always work? You know that there exist some of them which don't work at all.
What do you mean? Some.
Like if you should have taken 1 minus 2i and instead you took 1 plus 2i. Short of erasing plus and writing minus, you wouldn't get it by multiplying by unit.
Yes.
But how do you know that one of them has to be?
It should have a prime factorization.
Why? Why does it have to have prime factorization? What is it done?
That's what we're trying to prove. Like we know that there has to be some number with a norm of 5 that divides it.
Why?
We just know it. But we couldn't prove it.
Okay, alright.
And if we could prove that, we'd be much further along in proving what we
Okay, alright. That's accepted. Reach, move, sprint.
We also had to prime factorize
And with the
65. 65 was a lot
In the
easier
next slide.
because 65 is equal to 5 times 13. And we know how to get integers. That can be expressed in sum of squares because what we did with multiplying conjugates, we get their norm. We take, say, 2 plus I times 2 minus I, and there we get 5 times 13 is 3 plus 2i and 3 minus 2i, and there's 13. So that's easy enough. But then, this is our big question. How many Gaussian integers have a particular norm, and which norms are possible? So we really didn't spend that much time on how many have a particular norm, but on which norms are possible, we actually did spend quite a lot of time. This is where we found like a billion cool patterns. I'm gonna go through this a little. Okay, so first of all, I decided to look at these things in Mod 4. Squares in Mod 4. So in Mod 4, your squares are 0 and 1. So using these, you can get 0 plus 0 equals 0, 0 plus 1 equals 1, and 1 plus 1 equals 2. But you cannot get a 3 in Mod 4.
Matt says that any square is either 0 or 1 or 4. Okay.
Wait, what? Why?
That's
Where
not-
anything.
If it's
Oh,
0
haha,
mod 4,
just
it's
there's
square
only
is
like
zero.
Which
Sorry, yeah.
Yeah.
So there's no way to get a 3 in Mod 4.
So you never get 3 or 4.
So then I proved
The simplest proof in the world, but fairly amazing.
this was a lot easier
No
to draw
prime
on graph
thing
paper,
before, that was
which is why we
easy to
used
work
Dello.
It's like saying that
So I
instead of,
drew 4 boxes, and that's the one that explodes.
it's like saying that instead of,
Then I looked at it in Mod 8. In Mod 8, your squares are 1, 4, and 0. What?
saying that that they're all one, that it's possible to get 3 mod 4 is like saying that the primes in the set of natural numbers, it's impossible to have an even one other than 2.
So, using these, you can get 0 plus 1, 0 plus 4, 0 plus 0, and 1 plus 1, 1 plus 4, and 4 plus 4. So that's 0, 1, 4, 2, 5, and 0 again.
And we don't have a 3.
So the ones that we can't get are 3, 7, but you also have 6. 3 and 7 could have been anticipated. They're 3 mod 4, obviously you can't get them. But 6 is new. So, So we're going to put X's in 3 mod 4 boxes. That new symbol, a triangle, with 6 mod 8. So in this row, the new one was 3 mod 4. This one, 6 mod 8. Squares in mod 16. I'm not going to keep doing this for every mod. I have done it. You can kind of trust this because it's really awesome.
That's a very cool way to think, by the way.
I have this on graph paper and it looks a lot better, but I can't show that. So obviously, you know, that, and that get X. That gets a triangle and that gets a triangle. And this gets a circle. 12 mod 16. And I'm not going to keep drawing this picture. Draw it yourself. But the next new one, 24 mod 32. Next new one, 48 mod 64. Pattern? 3, 6, 12, 24, 48. Keep multiplying by 2. Next one, 96 mod 128. Each time you multiply your power of 2 by 2, you multiply your new one by 2. So I can tell you which ones are impossible, always in any mod power of 2 pretty quickly.
But you don't know how to solve them.
But the problem is, in say mod 32, 21 would be defined as possible, but you can't actually get 21. You can get 53 by taking 7 plus 7 squared plus 3 squared, and that's equal to 21 in mod 32. But you can't actually get 21 itself. So it's not foolproof.
But it's very, very good. If you get to the bottom of why is it that you can get something which is equivalent to 21 but not 21 itself, that's the heart of the matter. That's very, very cool.
Okay, so the next thing, Ms. Finkelstein suggested I look at this. I made a list of primes, and so the 1 mod 4s and the 3 mod 4s. So 1 mod 4 primes are like 5, 13, 17. 3 mod 4 primes are 3, 7, 11. And I looked at the squares in each of these boxes. 5, the squares are 1 and minus 1. 13, the squares are 1, 4, 3. 1, 3, 4, minus 4, minus 3, and minus 1. In mod 17, you get 1, 4, 1 and minus 1, 4 and minus 4, 8 and minus 8, you get a 2 and a minus 2, and that's it. You get each time, whatever you get, you also get minus that. And that's because you have a minus 1. Once you have minus 1, if you have a 4, you have minus 1 times 4, obviously has to be a square. In mod 3, there's not much. You get a 1. In mod 7, you get a 1, you get a minus 3, and you get a positive 2. You get everything that you can get, but either positive or negative. Mod 11, you get 1, 4, minus 2, 5, and 3. Always, you either get it or you get minus it, but never both. And that's where I was trying to go further on. Because if you get a minus 1, that's a square. You then know that there's some multiple. There's some square, x squared. And then you add 1 to that. And that equals, say, 17 times some x. And because this is a sum of squares, and this is where our other conjecture that we're sure is true but haven't proven comes into play. I should introduce that. We said that the number of x is equal to a squared plus b squared for a, b belonging to set of if, only if, x can be expressed as a square times primes 1 mod 4 and times 2 times 2 to the y, some power of 2, doesn't matter what, and times any number of primes 1 mod 4, I don't know how I express that. Times z sub 1 times z sub 2, where z sub, what's another letter? A. C. I already have it. Okay.
Good.
Sure. Wait, what's this say?
Product.
Oh, that's like some.
But-
We need to say that they're primes.
And,
We need to say that they're primes.
yes.
So you might want to say that it's the product of.
Okay. So then a product of a bunch of primes with a mod 4. Because basically what we're saying is it's only possible if all of its factors are in some way possible.
Uh-huh.
So like the number 50 is obviously possible, 49 plus 1. And that is 2 times 5 times 5. All these are possible. But then you get a number, say I wanted to look at 18. 18 is possible. No,
It's not.
Yeah.
It should be possible because
Yeah. But if you look at it, it's 2 times 3 times 3. And we've proven that 3 is not possible. But the key is that can be grouped as a square and all squares are possible.
Yeah.
2 is possible because it's 2. And we say that all primes will not, and the rest has to be a prime. Because if it's not a prime, it can be split into primes.
What prime?
2 is a prime, but it's not one of them.
It's an odd prime.
What?
It's an odd prime. It's an odd prime.
It's like 2% natural numbers, it's the only even prime.
That's right. It's odd prime because every other prime is odd. So
Yes.
odd not
Yes,
odd.
yes.
It's an odd prime. And
So
it's
if this, basically what we're saying is everything has to be expressible as a product of other possible things. Now, this m had better not have a 17 in it, or any factor of 17,
why?
because what we're saying is that m is in some number, we're taking it in mod 17.
Uh-huh.
So if we have to get up to 17 times 17, so if the square in mod 17 is 17 squared minus 1, I don't know how you're going to get there, because the biggest square is going to be this. I mean, it'll end up being 1, probably, but it will be 1. But the biggest actual number would be this, which is obviously less than that. So you'll never get up to 17. So basically, only where m is possible is this possible at all, regardless of whether 17 is. So m has to be possible, and 17 has to be possible. So that means 17 has to be possible, and you're good for if it has a minus 1. Ones without a minus 1, I was working on, but I'm pretty sure, but those are obviously impossible anyway, because they're all 3 mod 4s.
M
So-
has to be less than 17. I mean, it would be really nice if M is less than 17.
It has to be.
It has to be. Impossible.
Well, we're taking a number, in mod 17, so it's less than 17. We're squaring it, we're adding 1, and we're hoping that that's a multiple of 17.
Oh, yes, okay, all right.
So we're making,
Okay, you're right.
So that-
I'm thinking about the, yeah, you're right.
that's as big as we
You're
can
right.
get.
Yeah. You're right.
And this is about as far as we've gotten with Gaussian integers. We're extremely sure we're right, we just can't prove it. We tested,
So what's left to
we've
do?
actually tested every single prime up to 300 now.
So, guys, this is a chance for greatness. Prove it by yourself. This is a serious chance for greatness. Let's say simply what's left to prove.
What we want to prove, I've written this on the board before, is basically, you take a number that is 4k plus 4, where k is it?
Yep.
And you want to prove that m does not belong. They should be in it. M does not belong to the set of primes and Gaussian integers. So basically there exists a number a plus bi and a number a minus bi that equals your m. So basically a squared plus b squared equals m. And that's the only thing that can possibly divide it. So you want to prove that it's always the sum of squares of integers, or that it's never prime and Gaussian integers, something along those lines. There's lots of things that
What is the right sum of squares? Or something like that. Something like that.
We still have 4 minutes, so I'll say cool pattern that 2 things that I managed to prove about Pythagorean triples. Kind of very off topic.
That's cool.
So first, I've already looked at squares in mod 4. We've seen that they are 0 and 1. So these sum of squares have to be equal in a Pythagorean triple. So you can say 0 plus 0 equals 0, or 0 plus 1 equals 1, or 1 plus 1, sorry, this is mod 2, not mod 4. Or 1 plus 1 equals 0. No, it should be mod 4. It's mod 4.
Wait, what are you trying to do?
We're in mod 4. Squares are 0 and 1. So these are sides A and B, and this is side C in mod 4. So I'm just looking at it. So this is impossible because this 2 isn't a square.
Yeah.
This is possible. An example is 3 squared plus 4 squared equals 5 squared. And this is also possible, but these are obviously all even. Which means
You can bring it down.
they're all obviously, I can divide them all by 2. So this is never reduced. So this is the only possible reduced form.
Wait, isn't 2 just 0 mod 4 in your last example? I mean 0 mod 4.
Yeah, but we're mod 4.
So you know that one leg has to be odd, one leg has to be even, and the
Yeah.
hypotenuse will be
So
odd.
I find out.
Wait, that's true for all Pythagorean triples?
That's really cool.
Wait, so there's never 2 legs off?
Oh, no, there's more. Then in mod 8, the only squares are 0, 1, and 4. So if you want to get 2 of these to equal another one, and you can't have 0 plus 0 equals 0, or 0 plus, or 4 plus 4 equals 0, because those will all be reduced. The only way to do it is 0 plus 1 equals 1.
So you can say the previous what number is the middle line?
This?
No, middle line.
Wait, why is
4 plus 4 equals 0. They're all even.
Oh, okay.
We're
Yeah.
not 8, they're all even, that gets reduced. 0 plus 1 equals 1. So any odd is 1. Anything that's 2 mod 4 will give you a 4. 2 and 6 give 4. Anything 0 mod 4 gives the 0. So you know that actually B has to be divisible by 4, not just 2. So,
That's what shows me. What show?
and so I actually managed to come up with a way to generate every Pythagorean triple with a lot of work, but I can do it. What I take is I take my first multiple 4,
Yep.
say 4. I square it.
Continue.
So with that squared, I write this as the sum of odd numbers in every way. 7 plus 9.
Yeah.
That doesn't exist. Then I take 1 plus 3 plus 5.
Yeah.
Well,
That's so cool.
That'll get everything.
That is really cool. That is extremely cool. That is very cool.
And that's perfect.
So how do I stop this?